Hello and welcome to problem set 14. Our problems today will be from the topic An Introduction to Energy in Chemical Reactions. Before we get started, just a quick reminder that the worksheet that I will be covering today is available online through my website. And with that said, let's go ahead and get started with number one. Number one. Use the energy diagram below to answer A through C. And it's just a generic energy diagram with this general shape. Okay, so A, is the reaction endergonic or exergonic? So we can see that the energy of the reactants is lower than the energy of the products, meaning that energy must be absorbed in order for this reaction to proceed. And remember that a reaction that absorbs energy is an endergonic reaction. So for A, I'm going to write endergonic reaction. B, label the activation energy barrier, E of A. Okay, so let's do this in a different color. Let's go to the blue pen. Remember that the activation energy barrier refers to the minimum amount of energy required to get the reaction started. And in an energy diagram, it's given by this barrier here. Okay, so this I'm going to label E little a. Okay, so I'll put a little check on B because we drew the activation energy barrier, we labeled the activation energy barrier right on this diagram here. Okay, going on to C. How would you expect the energy diagram to change when a catalyst is used? So for C, let's write it right here. Remember that a catalyst is a substance that speeds the rate of a reaction without being consumed. And most catalysts work by providing an alternative pathway for the reaction, and that alternative pathway has a lower activation energy barrier. So the change in the energy diagram, let's go ahead and draw the catalyzed reaction in greens to make it stand out here. We would expect the reactants to be the same and the products to be the same, but the activation energy barrier to be lower. So we would expect a lower activation energy barrier, E of A, for the catalyzed reaction. Okay, and D. Is the reverse of this reaction endergonic or exergonic? So D, the reverse reaction going from the higher energy products here to these lower energy reactants, reversing this reaction. Remember that the reverse of an endergonic reaction is always going to be an exergonic reaction. And the amount of energy that had to be absorbed for that endergonic reaction to proceed will be equal in magnitude, but opposite in sign, to the amount of energy that's released in that reverse exergonic reaction. So we would expect the reverse reaction to be exergonic. Okay. And that finishes up number one. So going on to number two. Draw a generic energy diagram for an exergonic reaction that occurs slowly with a large free energy change. So we're going to be generic here, just really want to show the generic shape of the energy diagram. So I'm going to go ahead and label energy on my Y and reaction progress. on my x-axis here. So we are given that it is an exergonic reaction. So the generic shape is going to be something like this, okay? Where the energy of the products is going to be lower than the energy of the reactants, meaning that some energy had to be released in some form. And then we want to show more specifically that it has a slow rate, it occurs slowly, and has a large free energy change. So remember that the change in energy between those reactants and products is the delta G. And for an exergonic reaction, it's negative. We're trying to show that this is large. And then a reaction that occurs slowly has a larger activation energy barrier. That means that there will be fewer collisions that possess enough energy to get over that large activation energy barrier, and that's going to slow the reaction rate, lead to a lower reaction rate. So I'm going to go ahead and redraw this now that I've accounted for those things. Okay, so we want a high E of A, and we want a low energy for our product. So my final energy diagram over here, nice and neat. All right, E for energy. All right, Rx in progress. And we'll go ahead and indicate a large activation energy barrier and a large free energy change, delta G. Okay, so let's go ahead and label those things. We're trying to show that this reaction has a slow rate, so a large activation energy barrier, and we're trying to show a large change in free energy. So a negative delta G, we're trying to show that this is a large delta G. Okay, I'll go ahead and put that in parentheses. Okay, so still being generic. We don't actually have numbers. We're just showing generically what that exergonic reaction, which proceeds slowly and has a large delta G, would look like. All right, let's go ahead and erase here before we go on to number 3, so we have more room. Okay, number 3, explain why an increase in temperature increases the rate of a reaction. So remember that the temperature, as the temperature increases, the kinetic energy of the molecules will also increase. And so we know that there's a minimum amount of energy that is required to overcome that activation energy barrier. Well, if those molecules have a higher kinetic energy, then the collisions that are occurring between those molecules will be more energetic, and therefore more collisions will meet that minimum energy requirement and be able to overcome the activation energy barrier. So let's go ahead and put that in words up here on the board. So as the temperature is increased, the kinetic energy of the molecules will increase. And this will lead to more collisions occurring with enough energy to overcome the activation energy barrier. I'll just write E of A. All right, number 4. What is the difference between an exergonic reaction and an exothermic reaction? So I'll write exergonic reaction, I'll abbreviate RXN, and exothermic reaction. All right, so remember that an exergonic reaction is a reaction that releases energy. Whereas an exothermic reaction is specifically referring to a reaction that releases thermal energy, releases heat. So I'm going to write here, releases heat. So it's really not a good idea to use these terms interchangeably when you're referring to a process that releases heat. Specifically, the proper term is exothermic. But exergonic is a more general term, I guess you could say. It takes into account both the heat changes in a reaction as well as changes in entropy. So it is not always safe to assume that the two occur together. Although that is sometimes the case, it is not always the case. Okay, number 5. Let's go ahead and erase here before we go on to number 5. Number 5, photosynthesis occurs with a free energy change of positive 686 kilocalories per mole. During photosynthesis, carbon dioxide and water combine to form glucose, C6H12O6, and oxygen. A, write a balanced equation for photosynthesis. All right, so we are given all the information needed to write a balanced equation in the description on number 5. So we're told that carbon dioxide and water combine to form glucose, and you're given that formula, C6H12O6, and oxygen, O2. And so let's go ahead and draw a line down the middle. Let's do that in blue so we can balance this equation. All right, so on the reactant side we have 1 carbon, we have 2 plus 1, we have 3 oxygen, and we have 2 hydrogen. On the product side, let's write it in the same order. Remember that that is good note keeping. And so we have 6 carbons, we have 6 plus 2 for a total of 8 oxygen, and we have 12 hydrogen. All right, so I would not start with oxygen in this problem because you're going to have to get 4 coefficients correct in order to balance the oxygen. So that's going to be much more challenging than starting with, say, carbon, where you just have to get 2 coefficients correct. So I'm going to start with carbon because I can easily see that a 6 here will balance out my carbon. But that's also going to change my oxygen, so let's update to 12 plus 1, 13. All right, now let's go to hydrogen, because again, oxygen is going to be more challenging. So hydrogen, I can see over here, I have 12. So if I just put a 6 here, then that's going to update my hydrogen to 12 and my oxygen to 12 plus the 6. Okay, so 18. And now that my carbon and hydrogen are balanced, now oxygen is not so hard because we can see that we just need to make this number balance out to 18. So I'm going to go ahead and put a 6 here to bring this up to 12 plus the other 6 makes it 18. And I didn't have to throw my carbon or hydrogen out of balance to do that. All right, so we are balanced. So that is A. So let me write, oh, A is already written there. So let's go ahead and go on to B. Which is our final problem. B, draw an energy diagram for photosynthesis and label the following: activation energy, reactants, products, and the positive 686 kilocal per mole energy change. All right, so our energy diagram, I'm gonna write E for energy, and I'm gonna write Rx in progress for reaction progress. Okay, so we know that the free energy change, the delta G, write it over here, delta G is given as positive 686 kilocalories per mole. So hopefully you can deduce from that this, even if you didn't know already from photosynthesis, that this is an endergonic process or reaction. In order to proceed, this reaction must absorb energy. That means that the energy of our products is going to be higher than the energy of our reactants. So let's draw the proper shape for an endergonic reaction. Okay, so again, I know that because I'm given the free energy change, the delta G, as positive 686 kilocalories per mole. So I know that energy is absorbed. Remember that in this diagram, the reactants, let's go to a blue pen here for all the labeling. The reactants are represented by this first plateau. The activation energy barrier is represented by this incline here, this change in energy to get the reaction going, this activation energy barrier. And then the products are represented at the end. The energy of the products are this final plateau. Okay, so we've labeled the activation energy barrier, we labeled the reactants and the products. We now just need to label the Gibbs free energy, the change in Gibbs free energy. The delta G, remember, is given from the difference in the energy of the reactants and products. So the delta G, which is positive 686 kilocalories per mole, tells us how much energy has to be absorbed per mole of glucose for this reaction to occur. Okay, so this will conclude our problem set 14. I hope you will consider tuning in to tutorial number 15. Thank you.